Hello dear students, welcome back to NEET World. So we are discussing hydrocarbons for upcoming EAPCET 2026 right now. So these sessions are also useful for your NEET and JEE preparation. Okay, so today we will be discussing one of the very interesting and easy and most weightage topic for your EAPCET, because there will be a question for sure from this topic. So what is the topic? Aromatic hydrocarbons. Okay, so aromatic hydrocarbons is one of the very important topic for your EAPCET, JEE and NEET exams, especially when it comes to EAPCET. So there will not be any question paper without having a question from this aromatic compounds. Okay, so it is that much important. So it means you should not skip this topic, whether you are preparing very seriously or you just want to go with looking at the paper like very nominally. So but you need to know this topic for sure, because at least one question from this topic. Okay, so let us make it more clear by looking at the previous year questions as well as complete clear discussion of the concept. Okay, just follow the session till the end. See, ee question lekunda question paper undadamma. So it means if you see the previous papers, there will be at least one or two questions, like at least one question in your EAPCET exam. Okay, so I am saying this much confident means you just consider it as a very important topic. That's it. Okay, so first of all let me show you some questions first. See, these are some questions they are asking from EAPCET exam. See, these are some questions which are came in the last previous papers like 2022, 22, 21, 20. So these are some questions. Okay, so now you are going to solve all these questions with this session, within this session. Okay, so now just give me some time so that I will explain you everything clearly and you can get complete clarity and you can answer all those questions. Right, so first of all, see, I will be telling you the reactions, aromatic compound reactions once after learning about aromaticity, because aromaticity is important topic here first. Aromaticity. Okay, let me change the color. So here aromaticity is a property of organic compounds. What I am saying, aromaticity is a property of organic compounds. Okay, so now those organic compounds which are cyclic and unsaturated, what I am saying, cyclic unsaturated compounds will show this aromatic nature. Okay, now how can we identify whether a compound is aromatic or not? For example, I am saying this is cyclic. See, simply if I write like this, this is a open sign now, so this cannot be an aromatic now. So it should be cyclic one, next unsaturated. So now I am writing like this, it's a cyclic and it has one double bond. Can I say this is aromatic? No, this is also not the proper way of identification. See, there are some rules to be followed to identify these aromatic compounds. Okay, so what are those 4 rules? See, organic compound should be cyclic, and the next it should be have planarity, it should be planar. So it means carbon should be either sp or sp2 hybridized. Okay, there are some exceptional cases where it has sp3 hybridization also at some carbons, but it is aromatic. That's why I am indicating star. Okay, that should be what? Planar. Okay, I will tell you with some examples, then you will get more clarity. And third condition should be complete conjugation should be there. Conjugation of pi electrons. And fourth condition is it should obey 4n+2 pi electron rule. Okay, these are the rules you need to check. So what is this? N indicates, N can be like 0, 1, 2, 3, 4 like that, so on it can be. Okay, so if I put 0 equals to n equals to 0, then you will get 2 pi electrons. So these are aromatic numbers now. So 2 pi electrons or 6 pi electrons or 10 pi electrons or 10 pi electrons, or you can see 14 pi electrons. So these numbers containing species are aromatic. Okay, now let me give you some examples. See, here I am writing the first simple compound here is benzene. So look at this, it is a cyclic compound and all carbons are sp2 carbons right now. So if it is sp2, what will be the geometry? Trigonal planar, na? Trigonal planar you are saying. If it is sp, this is linear you are saying. So both of them are planar compounds only. Okay, so it means all carbons here are sp2, so I can say the compound is planar. Okay, and next, what about complete conjugation? Is these pi electrons are in alternate positions now, so it means whenever there is alternate position like this with planarity, they will conjugate in this way. Okay, so that complete conjugation is also observed here. Okay, so now what is its resulting resonating structure? So you will get a pi bond here shifting here, and this one. See the position of pi bonds, if you observe, it looks like difference right now. So it means you will get a resonance hybrid from this by considering position of pi electrons in first structure, and in second structure you can draw a resonating structure. What do we mean by resonating structure? The movement of pi electrons are taking place now, so that you can represent in this way, like this. So this movement of pi electron is represented in this way. So pi electrons are keep on moving in this cyclic ring now. So you can say this is the resonance hybrid. What is this? Resonance hybrid. In actually resonance hybrid. Okay, actually the molecule, an organic molecule will always be stays in this resonant hybrid form. These are the hypothetical forms. We are just writing them to understand ourselves. Okay, so in order to make the chemical reactions like approaching of electrophiles and nucleophile, understanding the reaction mechanism, we are using this imaginary or hypothetical resonating structure, but in reality molecule will looks like this. Okay, it means all the carbons will be having equal bond length in these things. Okay, right. Next, now what about this? It has planar, cyclic, planar, complete conjugation, and how many pi electrons you are seeing? See 1, 2, 3. So 3 pi bonds means each bond contains 2 electrons right now. So 3 to the 6. So you are getting 6 pi electrons. So 6 pi electron is what number here? So if you put n equals to 1, so 4 plus 2 is 6. So it is obeying all these 4 rules now. So benzene is our aromatic compound now. What you can say? Benzene is our aromatic compound. Okay, now aromatic compounds are highly stable. What I am saying? Aromatic compounds are highly stable. Why they are stable? They are stable because all the pi electrons here, whatever you are seeing, that lies in lower energy bonding molecular orbital. Where they lies? They lies in lower energy. All pi electrons, aromatic compounds are stable because the pi electrons lies in lower energy states. So what do we mean by lower energy states here? So this these pi electrons will be in pi bonding molecular orbital, where they will be pi bonding molecular orbitals. Okay, they are not in anti-bonding, they are in pi bonding molecular orbital. See, you have studied about molecular orbital theory in chemical bonding right now. So there we will be seeing whenever electrons are in bonding molecular orbital, those are stable. If you are filling electrons in anti-bonding molecular orbital, their bond order decreases, therefore it's become less stable right now. That's what I am saying here. All the bonding molecular orbital, all these pi electrons lies in pi bonding molecular orbitals, therefore they are stable. Now how can you represent their molecular orbitals? See, just take cyclohexane, like we can use a polygon rule here. So just draw a circle. Okay, so in this circle just draw it in this way. In this way. So now see, there are 6 carbons, so that we are getting like this hexagon you will get. So just write here, just divide this molecule into 2 equal halves now, like this. Okay, so here you can say 1 pi molecular orbital, and this is one more, this is again one more, here one more, and here one more, like this, here one more, like this. You get 6 pi molecular orbitals you will get. Okay, so now is there any carbon on this line? No carbon now, or no pi orbital lying in this line right now. So it means if any orbitals are lying on this line, then you can say those are non-bonding orbitals. What I am saying? Non-bonding molecular orbitals. Okay, if the orbitals are lower than this line, these are bonding molecular orbital. These are pi BMOs, pi bonding molecular orbitals. The orbitals which are above this line are called pi star. It means anti-bonding molecular orbitals. Okay, this is how you need to represent. Now how many electrons are there? 6 pi electrons. Now see, this is the lowest energy, this is lowest energy. Now see, this orbital is lowest, so you can fill 2 electrons in the lowest first, and the next here you are seeing degenerate states. Okay, how many are there? 2 are there. Now fill 1 electron here and 1 more electron here. Okay, there are 6 electrons, 4 electrons are over. Next, 5th electron like this. So again last 6th electron comes here, therefore all the bonding molecular orbitals are filled. Only lower energy orbitals are filled, now higher energy orbitals are empty. So it means whenever you are filling only in lower energy orbitals, those molecules are stable. That's why aromatic compounds are highly stable. And one more thing, you know, aromatic compounds have diamagnetic nature. Do you have any unpaired electrons here? No, no, all electrons are paired. That's why these are diamagnetic substance. Okay, remember this line also. These are diamagnetic and highly stable. Okay, so you can say diatropic also here. Okay, so these terms whatever I used is clear now. So you can say this is Frost-Muslin rule or polygon rule for explanation of molecular orbital diagram, or you can say diamagnetic or paramagnetic nature of the substances can be explained for this aromatic and non-aromatic compounds. So you got now what are the 4 rules to be remembered for identifying aromaticity, aromatic compounds, whether a compound is aromatic or not. See, it depends on these 4 rules. Compound should be cyclic, yes, then next it should be planar, then next it should have complete conjugation, next 4n plus 2 pi electrons should be there, then you can say it is aromatic compound. If any of this rule is not obeyed, then that becomes a non-aromatic compound. Okay, what I am saying, then it becomes a non-aromatic compound. Okay, now see one more rule I am saying here, the first 3 rules whatever you have seen, first 3 rules, what are the first 3 rules? Compound is cyclic, planar and complete conjugation. So these rules are obeyed, but instead of having 4n plus 2 pi electrons, if the substance, if the molecule has 4n pi electrons, how many? 4n pi electrons if it is having, then you can say it as anti-aromatic. What I am saying? Anti-aromatic. Okay, if it is having this kind of rule, then you can say anti-aromatic. Okay, so now let us draw one structure for this. See, I am writing cyclopentadiene, cyclobutadiene. Okay, like this I am writing. So now just look at this compound how it is. So it has 4 pi electrons, like 2 pi bonds. Each pi bond contain 2 electrons. Okay, so 2 pi electrons, 2 pi electrons, 4 pi electrons are there, and it is a cyclic, planar, and conjugation also there. If you observe in this, yes, we can get a conjugative structures in this manner. So this molecule is called anti-aromatic. So anti-aromatic compounds are highly unstable. What I am saying, these are highly unstable. So what is the reason for their instability? Because the pi electrons will goes to the higher energy levels. Which energy levels I am saying? Higher energy levels. Okay, so due to the electrons present in higher energy levels, those are unstable or less stable when we compare with the aromatic compounds. Okay, so now you got 3 things. One is aromatic, another one is anti-aromatic, another one is non-aromatic. Aromatic, anti-aromatic, non-aromatic. See, anti is different, non is different. Anti-aromatic means it should obey this rule. Okay, if any of these rules are not obeyed, then we can say then that compound as a non-aromatic compound. Okay, now let us take some examples and we will get complete clarity on this discussion. See, I am drawing all the structures here. Just tell me what about their each and every structure here. You need to answer all these things by solving these questions. Yes, almost your practice is done here itself. Yes, up to here let us try once first of all. So tell me here first one, what is the nature of first compound? Tell me whether it is aromatic, non-aromatic or anti-aromatic. Anyone in the chat box can answer me this. Up to here let us try once first of all. So tell me here first one, what is the nature of first compound? Yeah, so look at this. You have cyclic, yes, cyclic is fine. And do we have planarity at all the carbons? These two carbons are sp2, those are planar. But what about this? This is sp3 carbon now. So this is tetrahedral non-planar. This carbon is tetrahedral non-planar. So I can say this is a non-aromatic. Okay. Now what about this compound? See, it is having all carbons with cyclic compound, all carbon. This is carbocation sp2, sp2, sp2. So all of them are trigonal planar geometry. So it is a planar. Okay. And now here you have two pi electrons which are in conjugation. So what is a conjugative structure you will be getting from this? When it is shifting here, positive charge will be shifted onto this carbon. So here positive and here pi electrons like this. Okay, so complete conjugation is also possible here, because again this pi electron will shift here, you are going to get positive charge here, like that complete conjugation is possible. So how many 2 pi electrons are there? Yes, 2 pi electron is an aromatic number of 4n plus 2. It means if n value is 0, you will get 2 pi electrons. So this is aromatic. Okay, next what about this one? See, you have all carbons, carbon anion is sp2 and these two carbons also sp2 here. So what you can say here, because it is in conjugation, that's why I am saying sp2. So if it is in conjugation like this, so what happens? If it is in conjugation like this, you will get a negative charge here, pi bond there. So due to that reason, what happens? So you have cyclic, planarity, and a complete conjugation is there. Yes, complete conjugation is there. But how many pi electrons are there? So these are 2 pi electrons. Again, this is negative charge, means this is also 2 pi electrons. So totally 4 pi electrons are resulting here. So if it is 4 pi electrons, you can say this is anti-aromatic compound. What I am saying, this is anti-aromatic compound. Next, what about this compound? Is cyclic, planar, complete conjugation is also present, cyclobutadiene. So what is this? So it is also anti-aromatic, okay, like this you need to identify all the structures. Okay, now tell me about this compound. So this is, see here you have a negative and here is a positive. Negative means 2 electrons, positive means a vacant orbital, right now. So into that vacant orbital these electrons can be donated. So that is nothing but cyclobutadiene only, like this only you can write. So this is also becomes anti-aromatic. What I am saying, this is also anti-aromatic. Now what about this molecule? See, here negative, here also negative. And if you observe this negative charge in conjugation with this pi electrons right now. So if it is conjugating in that way, you are going to get a structure in this manner. Like pi bond here, negative charge here, this newly formed negative charge is here. Again this can also participate in conjugation. How it can be? So these pi electrons can be donated here and this negative charge shifts here. Like that you will get complete conjugation right now. So it means how many pi electrons are in conjugation? So these 2 pi electrons, and after that this bond is also becoming a pi electron. After that this bond also becoming a pi electron. So total how many pi electrons you are seeing? 6 pi electrons you are seeing. So it is a cyclic, a planar, 6 pi electrons are present with complete conjugation. So you can say this number as aromatic number right now. Just we have seen 4n plus 2 means n value you put 1, 4 plus 2, 4n means n is 1, 4 plus 2, 6 pi electrons is satisfied now. So this is aromatic. Okay, and the next here, look at this question. See, here you have 2 pi electrons. Okay, you have 2 pi electrons. After this positive charge, here also positive charge. Now these pi electrons are in conjugation with this vacant orbital and you will get a positive charges here. Right now again it will shift here, like this, again it will shift here like this. So now what you are seeing, complete conjugation is taking place and it having only 2 pi electrons. So 2 pi electrons means what? N value 0 you can take, so it is 2 pi electrons. So this is also becoming aromatic. What is that? Aromatic compound. So this is how you need to identify. I hope you now you got this like idea to like identifying the aromatic nature, right now. So if it is clear, just tell me clear in the chat box or click on the like button, so that I consider that you are really getting the clarity on this topic. Okay, now tell me about this compound. Those who are in the live session, please tell me about that compound which I am showing on the screen. Just tell me for this 5-member cyclic rings. Anyone who are watching online can answer me without taking any stress. So whatever the way you have understood, you please answer me based on that. Yeah, so let me explain you this. See, here you have 2 pi electrons here, compound is a cyclic, and here sp2 carbon only. So now if you observe, this is in conjugation, again you are going to get positive charge here, again this will shift here, you are going to get a positive charge here, like that complete conjugation is observed now. So it means it has 4 pi electrons in complete conjugation, and compound is planar and compound is cyclic. So all 4 rules are satisfied with 4 pi electrons. If the substance is having 4 pi electrons, we have studied now 4n pi electrons are present, then that compound becomes what? Anti-aromatic. What it becomes? Anti-aromatic. If you put n value as 1, so it will be 4 pi electrons. So it is anti-aromatic compound. Okay, this is how you need to identify. Now what about this structure? See, this is sp2, this is fine, but what about this carbon here? This is carbon with 2 hydrogen atoms right now. So it is sp3 carbon. If it is sp3, it won't involve in conjugation right now. So this is a non-planar compound which will stops the conjugation. So it will not allow the conjugation, it will not be having a complete conjugation. So you can say this molecule as a non-aromatic. Okay, what I am saying, this is not aromatic, not anti-aromatic, therefore you can call it as non-aromatic. Okay, non-aromatic. And the next, what about next example here? See, it has 6 pi electrons, complete conjugation is there, planar, so it can be a aromatic compound. What it can be? A aromatic compound like this. Next, tell me about these compounds, these 3 things. See here, these carbons are having pi bonds, but these are not in conjugation right now because they are separated 1 sigma bond, 2 sigma bonds. They should be in conjugative position only when they are in alternate position, like 1 sigma 1 pi, 1 sigma, see 1 pi sigma pi sigma pi, like that. But here it is pi sigma sigma pi, so it is not conjugative, so this is a non-aromatic. What I am saying, non-aromatic. What about this? So this is in conjugation here but not here, so you can say this is also non-aromatic, non-aromatic. What about this compound? It's a simple benzene now, so it is aromatic. We already discussed at the beginning of the session itself. Next, what about this compound? This is important, asked in exams multiple times. Now tell me, what about this compound, whether it is aromatic or non-aromatic? Very easy, you can easily answer. Check here once, cyclic compound, planarity is there or not, all carbons are sp2, yes. Then next, conjugation is there or not, yes. These pi electrons are shifting into the empty orbital of this carbon, like carbocation is there, no? It means vacant orbital is there, so you can shift here. So if it is shifting, you are going to get a positive charge on this carbon. Again here it will be shifting, you are going to get a positive charge here. Again this will be shifting here, you are going to get a positive charge like this. So it means complete conjugation you are seeing in this molecule or ion. So it means it has 6 pi electrons. How many pi electrons are there? 6 pi electrons are there. First of all, compound is cyclic and planar, and 6 pi electrons with complete conjugation right now. So it means what you can say, 6 pi electron is a Huckel number now, so it is a aromatic compound. What I am saying, it is an aromatic compound. Like this we need to identify. Now the benzene is there, so I am condensing 2 benzene rings, so that you are going to get a compound like this. You can call it as naphthalene. What I am saying, it is called as naphthalene. I hope you have used or you have seen these naphthalene balls. Okay, generally we will be seeing in toilets and all, no? So it is, those are nothing but naphthalene balls. So these naphthalene balls, whether it is aromatic or not, just check here. So 6 pi electrons here and 6 here, 7, 8, 9, 10. So 10 pi electrons are there right now. So compound definitely aromatic because it is a cyclic compound and all carbons are sp2 means planar, and complete conjugation is also present because these pi electrons are in common with this ring as well as this ring. So it means it is in conjugative position in this manner. Okay, so it means you can say it is an aromatic compound. What I am saying, it is an aromatic compound. Okay, Sai Ram in the chat box, aromatic. Hi sir, hi. Yes, hi dear. Next, one more structure I am writing, anthracene. What I am saying, next structure is anthracene. So just you condense 3 aromatic rings like this. So here so you can see that how it is like looking like condensed form of 3 aromatic ring, 3 benzene rings now. So it means this is called as anthracene. What I am saying, anthracene. Okay, remember the names, benzene, naphthalene, anthracene. Okay, so now they will ask which of the following is aromatic, means all these 3 are aromatic only. Okay, but which is more aromatic if they ask, because more the number of conjugations now, so more is the stability, or you can say more is the aromatic nature in case of anthracene, then naphthalene, and least is for benzene here. Okay, what I am saying, when you compare complete molecule, this ring, complete molecule, and this molecule and this molecule, so you can say anthracene is more aromatic. But you know, in anthracene how many rings are there? 1, 2, 3 rings are there now. In naphthalene 2 rings are there. Here only 1 ring. So if you want to compare aromaticity per ring, it means here you are having only 1 ring. Here also you take 1 ring. Here also you take 1 ring. So per ring if you compare, aromatic nature will be more for benzene. What I am saying, when you compare with individual rings, this is 1 ring, this is one more, like 1 ring here and 1 ring here. If you take like that, per ring aromaticity will be more for benzene, the next naphthalene, and least is for anthracene, like this. So overall aromaticity for molecule if they ask, anthracene is more aromatic, but aromaticity per one ring of that compound will be asked, means benzene will be more than naphthalene than anthracene. Remember the difference. Okay, remember this difference, very very important. Okay, the next, the next here, look at this compound. Yes, you can easily answer which of the following is not aromatic. Not aromatic. Tell me, how can you answer me that? Yes guys, you should answer in the chat box. Yeah. So tell me here, which of the following is not aromatic? Not aromatic means, see here you can see here you have pi negative charge, pi electrons. This is in 6 pi electrons. We discussed about this molecule. So it is a aromatic compound. What I am saying, aromatic here. Okay, we already discussed very clearly about this. Now what about this? See here, this ring is aromatic only now. That ring is aromatic only now. Yes, you can say this is aromatic. Okay, next what about this one? See, at least 1 ring you have aromatic ring. So it means at least 1 ring is aromatic, means compound is aromatic. So this is also aromatic compound. This is also aromatic compound. Okay, it means at least 1 ring should be aromatic in a given compound. So consider it as aromatic. Next, what about this? Yes, this is also aromatic. We discussed about this. Okay, we discussed about that. The next, phenanthracene. Phenanthracene is also aromatic. This is also aromatic. Okay, next what about this structure? Here you have a positive charge on this. Here you have a positive charge. So whenever there is positive charge in the given ring on the cyclopentadienyl cation, so this is anti-aromatic. So this is not aromatic, this is anti-aromatic. Here you have a negative charge. If it is negative charge, you can say this as a, see, pi electrons are there, negative charge. this is also anti-aromatic. So you can say E, F are anti-aromatic compounds in the given structures. What are the anti-aromatic compounds? E and F. Okay, that's it. Next. So look at this. Yesterday's discussion we have studied about alkynes right now. So based on alkynes, now you need to prepare benzene ring, aromatic ring. How can you prepare this? Very easy. Very easy. Look at here what they are saying. When propane is passed through a red hot iron tube at 873 Kelvin, the reaction gives a product having molecular formula. So simply you can take propane, you take propane here, CH3, C triple bond C, H. So propane having 3 carbons now, so it means if you take ethane like this and 3 moles you take, so this will get polymerizes at the temperature and pressure and gives you benzene ring, because acetylene, one molecule contains 2 carbons, and how many I am taking 3 to the 6, so that you will get a aromatic benzene ring here. Now here acetylene like propane contains 3 carbons now, just take this CC triple bond carbons and you can write methyl group like this. So now what happens is cyclization takes place here, cyclization takes place between these 3 molecules in this way. So when it is happening in that way, just look at here what is happening. So you are forming a 6-member ring like this, say double bond here and one more double bond here and one more double bond here, okay, and CH3 group here and one more here and here one. So like this we are getting now. So this is called mesitylene. What I am saying? Mesitylene. Okay. So this mesitylene is also an aromatic compound here. See, benzene ring with 3 1 comma 3 comma 5 1 3 5 trimethyl benzene, you can say 135 trimethyl benzene. So how many carbons are there in aromatic benzene ring? 6 carbons plus these 3 carbons of methyl groups. So you can write C9 and what about H? 3 plus 3 6 plus 3 9 10 11 12 H12 C9 H12. So you have option B is your answer for the question. Okay, so this is how you need to solve the question. So is this clear right now? Next, identify this total number of aromatic compounds from the below compounds. The given compounds are, check how many of them are aromatic. So the first one is called aniline. What is the name of this compound? Aniline. So aniline has benzene ring now, so it is aromatic. Now what about this one? Naphthalene. This is also aromatic. What about this one? Carbocation is there. We already discussed about this. This is anti-aromatic. Next, here there is no pi electrons in conjugation, only one single here. But these 2 carbons are sp3 carbons, non-planar. So this is non-aromatic. Okay, this is pyridine. So pyridine is aromatic. That's it. So 1, 2, 3. So option 3 will be your, option B will be your answer for the question, as it is having 3 as your answer. Now a few more questions I am adding here. Just tell me. Like this I am writing. So tell me, out of these 4 compounds which is aromatic, they will ask. See here, we know cyclopentadienyl anion is aromatic because here 2 pi electrons, like 4 pi electrons are there, 2 pi bonds, and this negative charge are in conjugation. So it will create negative charge and it has 6 pi electrons. How many it has? 6 pi electrons it has right now. Similar to that, if you observe it here, aniline nitrogen is also having electrons, those are also in conjugation now. So this is also 6 pi electrons are there. So it means this name of this compound is pyrrole. What I am saying, this is called as pyrrole, and this is called as thiophene. What I am saying, thiophene. Okay, thiophene lone pairs are there. Now see, here you are seeing two set of lone pairs, but only one lone pair. Every time remember, in conjugation from one atom, only one set of lone pair will be involved, not the other set, only one, not more than one. Okay, here also oxygen one lone pair is involving, and therefore in these molecules also you are getting 6 pi electrons right now. So this compound is called furan. So all these compounds are aromatic. Remember, all these compounds are aromatic only. Okay, these are called heterocyclic aromatic compounds. Remember, these are very important examples. You can expect a question from these structures itself. Okay, right. This is clear now, discussion is clear now. Next, non-aromatic compound among the following. Tell me which one is non-aromatic. See, a direct example from our discussion. The previous slide I explained, and in this slide we have a question on this thiophene. So tell me which is non-aromatic. Here you have cyclopentadienyl anion aromatic, and thiophene which is aromatic. Okay, and this is naphthalene aromatic. Next, what about this one? See, here you have sp3 carbon. This is sp3 carbon. 2 hydrogens are present, means this is sp3 carbon. So if it is sp3 carbon, non-aromatic. Right now, non-aromatic. So option non-aromatic. So option B will be your answer for the question. Okay, clear. So can you answer me this question? Anyone in the chat box can answer. Easy it is. Yes, anyone in the chat box can answer me. Yeah, we'll discuss this. Just hold on, because it is electrophilic aromatic substitution. So tell me about this. At least tell me about this. This is very easy. Cyclopentadienyl anion. This is from our discussion only. So cyclopentadienyl anion means this is a structure right now. Tell me whether it is aromatic, non-aromatic, anti-aromatic. See, it is 6 pi electron cyclic compound, planar, conjugation, everything is there. So it is a aromatic compound. And do we have any benzene ring? See, benzenoid compounds, non-benzenoid compounds are there. So benzenoid means at least its structure should contain one benzene ring. Okay, so do we have any benzene kind of ring? This is not a benzene kind of ring now. So it is a non-benzenoid compound. So you can say non-benzenoid compound and aromatic. Non-benzenoid compound and aromatic. So B is your answer for the question. Okay, right. Next. Tell me, identify the correct statements for a ring system to be exhibiting aromatic nature. So how it should be? It must possess 4n plus 2 pi electrons to be aromatic. Yes, this is correct. It must not be planar. No, it must be planar. Say it must be planar. So 2, 3 are correct. So it must possess 4n pi electrons. No, if it possesses 4n pi electrons, it becomes anti-aromatic. Right now, it becomes anti-aromatic. And if it is not must planar, then it becomes a non-aromatic. But they are asking about aromatic nature right now. So only B, C options are perfectly suitable. So it means, where do we have B and C? 2 and 3, 2, 3, 2, 3, 2, 3 is D. So D is your answer for the question. Okay, so this is how you need to choose the best options from the given options. Now tell me about this thing. Yeah, so now we need to discuss one more model question, like this kind of questions here. This kind of questions. See, aromatic compounds are there now. Aromatic compounds are there now. So these aromatic compounds having pi electrons right now. This is a benzene ring, means it's have a pi electrons right now. So pi electrons is nothing but these are more electron density species now. So now it can act as a nucleophile also in some reactions. It means these pi electrons can be donated to someone who is electron deficient. So that electron deficient species are called electrophiles. What I am saying? Electron deficient species are called electrophiles. Okay, so to this electrophile, these electrons can be donated. Why that can be donated? See, this is having pi electrons now it is looking for electrons. It is unstable and it will directly attack on this benzene ring. Therefore, what happens when it is attacking, it will give its lone pair like this pi electrons to that electrophile. Now what happens is, you are going to get a compound like this. See, this is donated now, so here you are adding electrophile and here you are creating positive charge. See, on each carbon if you observe, there is one hydrogen atom already attached like this. Okay, on each carbon it will be like this. Okay, now when these pi electrons are moving, you are getting a positive charge here now. So the wherever the carbon, like on which carbon, like on the carbon that we added this electrophile, already hydrogen atom present now, that hydrogen atom is removed now. Why it is removed? See, initially benzene is aromatic, this is aromatic right now initially. Now here if you see, this is becoming non-aromatic compound. What I am saying, this is non-aromatic compound. Okay, so now this compound whatever it is formed here will be called as a sigma complex. What I am saying, it is called as sigma complex. So what is that? Sigma complex, or you can say carbocation in simple words. Okay, remember this term which I am using here, because there is one question I will show you. Okay, so this sigma complex is stabilized by conjugation of these pi electrons like this. Okay, when it is shifting here, positive charge will be coming here, again this will comes here, like that it will be stabilized and a non-aromatic compound will be getting stabilized in that way. Okay, so now what happens is, this sigma complex again have more tendency to regain their aromatic nature by losing this proton from here. So if it is losing that proton, it will regain its aromatic nature and becomes a compound like this, and in this position you have electrophile. Okay, so this is aromatic compound, in the place of hydrogen we are substituting electrophile right now. So this is what, in the place hydrogen atom is replaced by electrophile right now. So you can say electrophilic substitution reaction. What you can call electrophilic substitution reaction. It is happening on aromatic ring now. So aromatic electrophilic substitution reaction you can say. So what you can say, aromatic electrophilic substitution reaction. Okay, so in the same manner, so just look at this question. Look at this question, what they are saying, the product Z of the following reaction is, what is the product Z in the following reaction? So now what happens is, this methyl chloride and this anhydrous AlCl3, so that will react to generate a carbocation, CH3Cl plus AlCl3. Okay, here vacant orbital is there not, to that lone pairs will be donated. So chloride ion comes out and that will be giving AlCl4 minus and CH3 plus. So what is our electrophile? Methyl carbocation. So that will be goes and attack on this benzene ring. So one of this position of this benzene ring will be taking this methyl group and hydrogen atom is removed. For example, here hydrogen atom from here can be removed and replaced by methyl, so that you get option B as your answer. Hope our discussion is clear. Now I will be giving you one question as a practice question. Just tell me your answer for this. See, these are the questions I just wanted to show you. Okay, now particularly you can try this above question and below question on your own interest, but we will discuss them later. But you just read this statement, which are the following statements are correct. So based on the 4 statements, please mention your correct answer from these 4 statements. All these things are from our discussion only, except like when nitric acid nitration is taking place, nitric acid acts as a base, not as an acid. Okay, I told you this one. Just look at these 2 things and tell me your answer in the comment box. Okay, hope you got this lecture, and I hope it is really helpful, and thank you for watching. You can share with your friends. Thank you.